Hi, this is Pixelated Plasma, and today we are building a simple peer-to-peer game using Bevy and Iroh. So why I'm building this? Well, I've been interested in learning Rust for a while, and I've been trying to think what project to build. And I played with P5JS a little bit a while back, and I really like that kind of graphic programming, which is like simple. So I wanted to try out some real game engine like Bevy, and peer-to-peer sounds fun. I've learned a little bit about it, learning about Iroh, so thought this would be a nice project to make. The point here is not to make an amazing game in Bevy. It's going to be a very minimal game. The point is to learn how peer-to-peer networking can work in a game like this. As far as I know, I think Factorio and some other games use stuff like this to have their multiplayer setup. So it probably has some utility in the real world. How you build a simple Bevy app is very simple. You just create a new app with two systems, set up and an update, and the update setup just creates a new circle, which is your player. And on update, you're just moving your circle around using keys. This is kind of what the game looks like. But the crux of this is how do you set up the peer-to-peer, right? Because on the internet, most likely you do not have a public IP. You sit behind an ISP, and what happens is you send your request to your ISP. Your ISP has a public IP, and it creates a port mapping to your IP and sends out the request out in the public internet, and on any response on that port, it sends it back to your computer, right? But the problem is if your peer is also behind an ISP and you're behind an ISP, you both can't talk to each other. And to get around this, what you can use is called UDP hole punching. What essentially happens is you have a public server called a stun server, and you send your request to the stun server. The stun server now gets your public IP, your ISP IP and a port, and your friend does the same thing. And then the stun server kind of exchanges information, right? It tells you about your friend's IP and your friend about yours. And then what you can do is you can try to send a request directly to that IP and that port. And that's kind of the meat of how this works, but there are videos that I've attached in the description on how this works a lot better, because there's some more complexity to it. But then I'm going to use Iroh to abstract all this away. And how Iroh works is based on essentially two pieces of information. It's an endpoint. This endpoint is imagine your local server, right? It's what is your identity in the public internet, and it works. And then for the gossip, it needs a topic ID. Topic ID is where you're sending messages and where you get messages from. In the app itself, you have kind of two functionalities, right? When you're setting up your app, you create a new network, and then as a friend, you can join your friend's network. And the messages themselves are pretty straightforward. You just have this Iroh message struct, which has the endpoint is not necessary here because you get it even as a part of the response. The message here is what actions your application is trying to take. Here we just have very simple application actions that are add another player and send position. And you need these nonce because Iroh actually deduplicates your message. So let's say you're not moving, right? Your player is at the same location. If it's at the same location, it's going to send a bunch of messages with the same information, and you kind of want to receive all messages and on the application layer decide if you want to discard them. So that's why you add this nonce so that all messages come to your application and then you can discard, because I kind of use this information, right? Sending the same location, but still it's necessary to get that message. And okay, so now the next problem that happens is Bevy, how it works is you give it a bunch of functions and Bevy decides when to run them. So for example, you give it a setup function, an update function, a run on status function, a run on status transition, or stuff like that. But Iroh itself is a networking application. So for Iroh, you don't want Bevy to decide when to receive messages from Iroh, right? And a way to do that kind of stuff, the async stuff, is Tokyo. But you can't spin up Bevy in a Tokyo runtime. So what you can do is you can have your core application main thread run your Bevy game, and you can spin up another thread that has a Tokyo runtime, and this Tokyo runtime then does the Iroh networking, and then you can have a network bridge which you can use to send messages to Bevy and get messages get message back from Bevy. And how this would work is something like this, right? You would have a network worker which will have a Tokyo select. A Tokyo select is like, okay, it has multiple streams and it will pick up whichever one gets a message first. So, and then you'll have these receiver and sender channels. They are, the way I think about them is like Go channels, might not be accurate here, but it's a nice thinking pattern where you can send stuff here and then the receiver will receive it when it wants to. And so this way, the Bevy is going to send events. Hey, I clicked on create, so create a network, and Iroh can send this user got added, so add him to the game, stuff like that. And on the other side, we'll have a Bevy receiver function. This is what is going to run once per update and take events from the network and do what it needs to do with them, like add player or update position. And the events themselves are pretty simple. You have like these two kinds, right? From Bevy to Iroh and from Iroh to Bevy. And they're like fairly simple. You create a new game. When you send Iroh layer the create task, it is going to return a ticket to you that you have to expose to the user so that he can share it with his peers to actually join the game. There is joins, peer left and stuff like that. And the message itself is like we saw before, an add and a send position. So now, how do you identify a player uniquely is from the endpoint ID. Like I said, it's like your unique user ID or something like that. And you can track them in a global resource so that you can check, oh, this user has left, this user has been added, and whose position to update when you get the send position. And this is what the final game kind of looks like. You create a new game, and when you click create, it gives you a ticket. You can use T to copy it, and then the peer has to paste it. And when you paste it, you both are like in the same network now and running. Even though this is running on localhost, you can actually in theory be anywhere on the public internet and this will still work. And I find that to be pretty cool. It requires no server. I have the source code and a bunch of links on how these technologies work in the description. Feel free to check it out, but I'm new to Rust, so might not be that super great of a code. Thanks.